Okay, welcome. This is part one of circular motion, and we're going to be looking at the kinematics portion of that. First off, let's define what kinematics means of uniform circular motion. So uniform circular motion, abbreviated UCM, is when an object moves in a circle at a constant rate. That means it goes around in a circle and goes at the same speed. The distance that the object moves is, of course, the circumference. The time it takes to go around one time is called the period. So we'll refer to that. And there's one more measurement that comes up, which is the frequency. So the frequency is the number of revolutions per second, or we could actually do revolutions per minute. But revolutions per second has a special unit called the hertz. So we're going to be doing some calculations of kinematics, and so kinematics, of course, is distance, time, velocity, acceleration, and such. So we simply take the definition of velocity, which is distance over time. We replace the distance with the circumference. So the formula for circumference is 2 pi r. And the period, which is the time it takes to go around once, we normally use a capital T for that. And the relationship between period and frequency is such that the frequency and period are reciprocals of each other. So obviously, if you know one, then you know the other. So let's just jump right into an example problem. How fast is a 100-gram ball on a string that is whirled going if the radius of the circle is 0.5 meters and it takes 1.4 seconds to complete the revolution. So we're given the mass, we're given the radius, and then we're given the time for one complete revolution. So we simply just take that formula that we just learned, velocity equals 2 pi r over t, and we can plug that in because we have the radius of 0.5 meters. We want to make sure we're in meters and seconds, so our units come out, and the period is 1.4 seconds, so that comes out to 2.24 meters per second. Pretty straightforward. Notice that in none of these calculations am I including the 100-gram ball. So the question then, how fast would a 100-pound ball be moving in the same situation at 0.5 meter radius in 1.4 seconds? Well, it would just be 2.24 because the mass is not figured in this formula. Next question, what is the frequency if the length of the string is increased by 0.75 meters? So now, or rather increased to 0.75 meters, and it goes the same speed. So now we simply have to take this formula, velocity equals 2 pi r over the period, and we're going to solve for period. So we're going to multiply both sides by t, and then we're going to divide by v, and so we get 2 pi r over v to get our period, and we can plug in the values there. So we have the radius of 0.75 and the velocity of 2.24 that we just calculated, and that comes out to 2.1 seconds. Because the radius is larger, then it takes longer to go around one revolution, because it has to go around slower, or not slower, but takes more time rather. And the next question is what's the frequency? So the frequency is reciprocal, and so we simply put 1 over 2.1 seconds. That comes out to 0.47 revolutions per second, and then we can label that as 0.7 or 0.47 hertz. So those are pretty straightforward questions. Those are the basis of the kinematics. But there's one more thing. What about acceleration? So we have this ball on a string going around, and we have a velocity at one point pointing off to the right. We have a velocity at another random point pointing off there. So even though the magnitudes are the same, is it, the magnitudes would indicate the speed, so is this accelerating? The quick answer to that is yes. Since the direction is changing, then we say that it's accelerating. So up to this point, the linear kinematics, in order for something to accelerate, then we would change the speed, either speed up or speed down. But now the speed is remaining the same, but the directions is changing, so we say it's accelerating. So whereabouts would that acceleration be? Well, if we take this v and we subtract that v, if we put that on the end of this, it would point back this way, and then we would have the acceleration, or the change of velocity, pointing towards the center of the circle, and then so does the acceleration. We label this acceleration with the subscript c to indicate that it's centripetal acceleration. So that word may be new to you. Centripetal is defined as center seeking, and so we have this situation where the change of the formula comes out to the centripetal acceleration is v squared over r. So this refers to the speed squared over r. We won't go into how we derive this formula this time. Maybe we'll show that later. But you can see that throughout the circle that the acceleration is always going to point to the center of the circle. Okay, so now let's look at the dynamics of uniform circular motion. The dynamics means we're going to look at the forces involved. And we are going to, of course, use Newton's second law, but we're going to apply it to a circular motion. So we simply take the Newton's second law, sigma F equals ma, and we just subscript it with a small c. So the centripetal force is equal to the mass times the centripetal acceleration. And so the force is also directed towards the center, centripetal again meaning center seeking. So the one thing we have to look for every time we're dealing with the centripetal force is what causes the motion. In this case, it would be tension of the string would cause the changing direction of the ball, right? So there's this constant tension going on in the string and the ball, so we're sort of pulling the ball towards the center of the circle all the time. I threw in the word gravity because we don't always have a string when we have something going around. So if we put the Earth in the center and we have the moon going around us, it would be gravity that's causing that centripetal force. We will definitely look at that later on in this chapter. But right now we're going to focus in on things like balls on strings. Just for your information, there's no real centrifugal force, and that would be the opposite force from the tension, or some sort of force that's pushing away from it. Centrifugal actually means center fleeing, and there's no real centrifugal force. That word is used a lot, centrifuge, which is something that separates large particles from small particles. But in physics, their centrifugal force is actually a false force. Okay, so here's a thought idea. So we have this ball on a string going around in a circle. The velocity at this moment in time is labeled here. If right at that particular moment the string was cut, that means there's no more tension on the string. Which way will the ball go? Ponder that. Pause the video if you need to. Well, of course, it's going to go exactly the direction that that velocity is at that moment. And so the velocity is tangent to the circle, so that ball would fly straight along that line. It's not easy to demonstrate, but perhaps I will in class. Okay, so now we're going to look at motion in a horizontal thing, and that's when we have a situation like this. So we're holding a string, we're whirling this ball around, and so we have the tension that is causing the centripetal motion, or the force required to keep it turning around. But we also have the weight that is downward. So we actually don't get this exactly horizontal, because there's just always this weight. No matter how fast you whirl it around, you're always going to have weight pulling it down. So the question about how fast does it have to go to be perfectly horizontal would be, there's no such speed available that would cause this string to be perfectly horizontal, because technically there's always a force pulling down. And I know when we use it, we do it in class, or we whirl things around that way, it looks like the string is perfectly horizontal, but there's still that weight pulling downward. Okay, so let's take a look at an example. This picture is looking down on the person that's whirling it around. So this is a horizontal motion. Well, that's not true, because we're going to be looking at a vertical motion now. So this is a person's hand, and this is going up and down. Sorry, I thought I had another example of that. So what we're going to try to do is, what is the minimum speed at the top that we are going to whirl this around to keep it going in a motion. We don't want it to slack right there, and we don't want it. We want to find the minimum speed to keep it going at the top. So what we're going to do there is, we're going to the sum of all forces are now gravity and the tension are in the same direction. Right? So at the top, this tension is towards the center because it's on the string, and gravity is pulling it down. So we're going to look at an example like that. What about at the bottom? Well, at the bottom, we have the tension and the weight are in opposite directions. So we're going to end up subtracting those. We'll see how that plays out in the upcoming example. So let's take a look at that. So we have a ball on a string, and it's revolved in a uniform rate in a vertical circle. That means it goes going up and down with a radius of 72 centimeters. If the speed is 4 meters per second and its mass is 0.3, calculate the tension on the string when the ball is at the top and the bottom. So we'll first look at this, a picture of that. So we are going to calculate the tension on the string at the top. The string is drawn very lightly there, so you can't quite see it. So the top, we're going to take the sum of all forces is the tension plus gravity, and that's going to cause this centripetal motion. And so we set it up this way. So instead of saying MA, we're going to say, we're going to plug in the mass times the acceleration. So it's M, the acceleration is v squared over r, and the tension is the thing that we're calculating here. So that's our unknown, and mg, of course, is thusly. And so what we're going to do is we are going to end up subtracting the weight from the centripetal acceleration. Now I know this looks this doesn't look intuitive. These are not the two forces that we're looking at here, because the tension is what we're calculating. So that's in the same direction as the weight. This centripetal acceleration is what's causing it to go in a circle. So we have mv squared over r minus mg. We plug the numbers in. The 0.3 kilogram goes into the mass. The 4 is the speed it's going around, and the 0.72 in meters. So we take the centimeters, move the decimal over twice, we get 0.72. Minus 0.3, which is the mass, and gravity 9.8, and that calculates. You can pause it and do your own calculation, and that comes out to 3.7 newtons. Okay, so keep that in mind. We're going to now calculate the force at the bottom. Now what I want you to do is think about what do you think it's going to be? Is our calculation going to be the same, 3.7, or is it going to be more, or is it going to be less? Okay, so let's take a look at the bottom now. So we now have the tension minus gravity because they're in the opposite direction. That's causing centripetal force. So we plug that in, and notice this looks just about the same as before, except it's subtract. So now we're going to move this over, and we're going to move it over by adding it. So we're going to end up plugging these same numbers in, and we're going to end up adding the two. Now remember, we don't put a negative 9 point in there because we're dealing with the directions with the subtract. So you can't do both. You can't do a subtract and then subtract a negative because that won't work there. All right, so when we calculate that, you can pause and calculate, and it comes out to 9.6 newtons. Yeah, that's more than double. And it makes some sense. If you were the ball and you were going around, you would be almost weightless up there. You wouldn't feel as much tension up there as if you were down at the bottom here. Okay, I hope that makes sense. All right, there's one more type of problem we're going to look at, and that is when we have a car on a track. We're going to look at a car. So we're looking at it head on, and this car is going around the circle track. And so we've got friction causing the centripetal motion. Hope that makes sense. These two forces, of course, cancel each other out. This is on a flat track, by the way. This is not a banked one. We perhaps will look at a banked one a bit later. So we are going to set it up as the sum of all forces, which is equal to the centripetal force. Notice that once again, the normal force and gravity cancel each other out, so we don't even consider those. So we simply just say the friction is equal to the centripetal force, or the friction is what's causing it to go in a circle. Okay, so the formula for friction is, of course, mu mg, because it's not on an incline, and the centripetal force is mv squared over r. And notice there's an m on both sides, so I like to cancel out the m's, bring the g over as the denominator, and so this does not depend upon mass. So we simply take the speed squared, divide it by product of g and r, and then we get the coefficient of friction. All right, let's try one. So what's the maximum speed with which a 1,050 kilogram car can round a turn of radius 77 meters on a flat track if the coefficient of static friction of the tires and the road is 0.8. We use the static because, remember, kinetic friction is already sliding. Static friction, it's not. So picture looks like that, and we're looking for the same thing we did before. So we start out with the friction. It causes the centripetal force. Plug that in. We don't need the 1,050 kilogram. You can cancel those out. We're solving for the velocity, the speed. So I'm going to multiply by r. That's going to move that over there. Cancel out the m's, and then that'll give me v squared. And then I'm going to square root that. So actually, it's square root of mu gr. Once again, the mass is immaterial here. So go ahead and plug those numbers in. Do your calculation. Minimum speed is 24.6 meters per second. You could figure out what that is in miles per hour if you wanted to. Okay, so that's as far as we're going to go on this. We're not going to cover banked curves at this point, but perhaps we'll throw that in maybe next week. Okay, if you have any questions, you can make comments on this video, or you can contact me in the usual manner. Thank you for watching.